Hello, future engineers. Welcome to my YouTube channel. If you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. And to keep me refreshed, energized, and inspired, don't forget to subscribe. That's the only way you can help my channel. So here is example 168 by double integration method by three-moment equation. Determine the following: the slopes at A and B, the vertical reaction at B, and the bending moment at B. EI is constant. So here is the figure. So we will call the reaction at A as RA, reaction at B as RB, and reaction at C is RC. So there are two unknowns here, AX and AY, but AX is 0. One reaction here and one reaction here. So this beam is indeterminate to the first degree, and there is expected slope here. So if we apply double integration method, there will be two equations in two unknowns. So we can manage to solve this. So first, let's express RB in terms of RA to reduce the number of unknowns. Summation moment about C equals 0. So RA times 10 plus RB times 4 equals 50 times 2 plus 30 times 6. 3 plus 4 is 7. So 30 times 6 times 7. So expressing RB in terms of RA is negative 10 over 4 or negative 2.5 RA plus 340. So we then extend the loading to have a singular function for the elastic curve of the beam. Then we have EIY double prime, so call that X. EIY double prime equals moment equals RA times X plus negative 2.5 RA plus 340 times X minus 6 plus moment of this upward loading 30 times X minus 6 times X minus 6 over 2 or plus 15 quantity X minus 6 square minus 30 times X over 2 or 15 minus 15 X square minus 50 times quantity X minus 8. So take note that there is slope at A, but there's no deflection at A. So C sub 1 has a value, but there is no C sub 2. So integrating once, EIY prime equals RAX squared over 2 plus quantity negative 2.5 RA plus 340 times quantity X minus 6 squared over 2 plus 15 over 3 is 5, quantity X minus 6 cubed minus 5X cubed minus 25X minus 8 squared plus C sub 1. Integrating again, AIY is RAX cubed over 6 plus quantity negative 2.5 RA plus 340 quantity X minus 6 cubed over 6 plus 5 over 4 quantity X minus 6 raised to 4 minus 5 over 4 X to the 4th minus 25 over 3 quantity X minus 8 quantity cubed plus C sub 1X. So as I said, there's no C sub 2. So boundary condition when X is 6, Y is 0. So 0 equals RA 6 cubed over 6, 0, 0, minus 5 over 4, 6 to the 4th. Ignore because this is negative plus C sub 1 times 6. Simplifying, 6 cube over 6 is 36 RA plus 6 C sub 1 equals 1620. Call that equation 1. Then X is 10 at C, Y is 0. So 0 is RA 10 cube over 6 plus quantity negative 2.5 RA plus 340 close times 4 cube over 6 plus 5 fourths times 10 minus 6 is 4 cube. So 5 fourths 4 to the 4th minus 5 fourths 10 to the 4th minus 25 over 3 2 cube plus C sub 1 times 10. So simplifying again to formulate the second equation, so we have 140 RA plus 10 C sub 1 equals 8620, where 140 is 10 cube over 6 minus 2.5 times 4 cube over 6, so 140. Then for the constants, 8, 6, 20. Solving these two equations simultaneously, we can now have Ra equals 74 kilonewtons and C sub 1 equals negative 174. Then take note that when C sub 1 is divided by EI, it is the slope at A, because if you substitute it here, EI, y prime is the slope. When x is 0, everything here will be 0 or ignored. Then what is left is C sub 1. So C sub 1 is theta I. C sub 1 is divided by EI is C sub A. Is theta A, rather. Then for theta B, we set EIY prime, the value is x is 6, and since we have found RA, so substitute here. So EI theta B is 74 times 6 squared over 2, this is 0, 0, minus 5 times 6 cubed, 0 plus C sub 1, which is negative 174. So this is ignored. This term is ignored because when x is 6, this is negative inside the parentheses. So theta B is equal to 78 over EI. Then for the vertical reaction at B here, so it is negative 2.5 of RA 174 plus 340. So RB can now be found. It is equal to 155 kilonewtons. And finally, the bending moment at B. Take note, EIY double prime is moment. So we just set x is 6 because B is 6 meters from the origin A. So EIY double prime moment at B is RA 74 times 6, 0, 0, minus 15 times 6 squared, and this is ignored. So MB is equal to negative 96 kilonewton meter. So that's it for double integration solution. Then for three-moment equation, so remember the general three-moment equation is MA, MA is equal to MC equals 0, and the reference horizontal line is through B. It crosses A and it crosses C because A and C are supports that are unyielding. So the horizontal line through B, which is also a support, will cross A and C. So HA equals H sub C equals 0. Then the general three-moment equation is MA LAB plus 2MB quantity LAB plus LBC plus M sub C LBC plus quantity area 6 area 1 A over LAB plus quantity 6 area 2B over LBC equals 6EI quantity HA over LAB plus H sub C over LBC. So since MA 0, MC 0, the value of 6A1A over LAB for this uniform load is WL cube over 4, 36 cube over 4, while the value of 6A2B over LBC is PB over L quantity L squared minus B squared, where P is 50, B is 2 over L 4, quantity 4 squared minus B squared, 4 squared minus 2 squared. So substitute 0 plus 2MB quantity 6 plus 4 plus 0 plus 30 times 6 cube over 4 plus this one is 50 times 2 over 4 times quantity 4 squared minus 2 squared equals 0 because HA and HC are all zeros. So we can now solve this value. 1620, this one is 300, so negative 160, negative 300 divided by 2 times 1020. We can now solve MB equals negative 96 kilonewton meters, just like that. Then, having found MB, let's solve RB by statics. So let's have the free body diagram, apply MB. Because MB is 96, so it should be applied as shown. That's negative 96, so counterclockwise just to the right of B and clockwise just to the left of B. So that's negative to cause negative bending. Because at the left, supposedly, the moment is clockwise, at the right is counterclockwise. But because this is negative, so that means it is clockwise at the right section. Similarly, for the left section, the positive moment is clockwise at the left section for BC. And since this is negative, it should be applied counterclockwise as shown. So we will call the reaction component of B as RB left and as RB right as shown. Considering AB first, we sum up moment about A equals 0. So counterclockwise positive. So RA, RB, R sub C, where RB is RB left plus RB right. So summation moment A equals 0 considering AB. RB left times 6 equals 96 plus moment of load 30 times 6 times 3 about A. So RB left is equal to 106 kilonewtons. Then for BC, summation moment C equals 0, clockwise positive, so RB right times 4 equals 96 plus 50 times 2. So RB right is equal to 49 kilonewtons. So RB left plus RB right, 106 plus 49. So R sub B is 155 kilonewtons. So for the slopes at A and B, remember this is the beam, and we solve for RA first, and we plan to have the moment diagram by parts for the portion AB and apply area moment to solve for the slopes at A and B. So RA times 6 summation moment about B0 considering AB plus 96 equals 30 times 6 times 3. So R sub A is 74 as before. Then we draw the moment diagram by parts. So RA 74 times 6, that's 444 over EI. And the moment of the load, 30 times 6 times 3, second degree, that would be 540 over EI. So this is second degree. The location of the centroid is, for the triangle, 1/3 of 6 is 2. And therefore this is 2/3 of 6, 4. For spandrel of parabola, second degree, the location of the centroid is 6 over degree plus 2, so 6 over 4 or 1.5. And therefore this distance is 6 minus 1.5, 4.5. Then for the area of the triangle, 1/2 of 6 times 444 is 1332. And for the area of the spandrel, 1/3 of 6 times 540 is 1080. So remember that the division of B relative to A is the moment of areas between A and B with respect to B, while the division of A relative to the tangent at B is the moment of area with respect to A from area moment theorems or method. So this is the beam, and let's draw exaggerately the elastic curve later. So EI division of B relative to A is the moment of area with respect to B. So 1332 times 2 minus area of spandrel is minus, times 1.5. So division of B relative to A is equal to 1044 over EI. Since it is positive, the point B on the elastic curve is above the reference tangent at A. So let's now draw the exaggerated elastic curve of the beam portion AB. We draw the tangent, so point B on the elastic curve is above the reference tangent at A. So this is deviation of B relative to A, which is equal to 1044 over EI. And this is theta A. Since theta A rotates, the tangent at A is clockwise from the horizontal axis of the beam, and clockwise rotation is negative, therefore theta A is negative. So theta A is negative opposite over adjacent. So theta A is negative 1044 over 6 EI. So that's why theta A is equal to negative 174 over EI. Finally, EI division of A relative to B is moment of area with respect to A. So 1332 times 4 minus 1080 times 4.5. So solving for division of A relative to B, it is equal to 468 over EI. Since this is again positive, point A on the elastic curve is above the reference tangent at B. So let's draw the tangent at B, and therefore A is above this reference tangent because this is positive. So that's division of A relative to B, which is 468 over EI. Since theta B is, the tangent at B is counterclockwise from the horizontal as shown, and theta B is positive. So theta B is opposite over 6 again. So theta B is 468 over 6 EI. That's why theta B is 78 over EI. So that's it, and I hope that my explanation is very clear. It is just an application of area moment theorems.